If you have ever bought a BLE module, you have seen the number 100 meters, 300 meters, some of them say a kilometer, a few of the more optimistic ones say more than that. All of those numbers are in a technical sense correct, and in any practical sense they are completely disconnected from what your module will actually do when you deploy it. I want to explain why, not to complain about it. The manufacturers are not necessarily lying, they are just measuring something different from what you think they are measuring. Here is what they are actually doing. They take two modules, they place them in an open field or an RF anechoic chamber, or sometimes just a very long corridor, no obstacles, no interference sources. They orient the antennas at exactly the optimal angle relative to each other. They set the transmit power to maximum. They measure the distance at which the packet error rate crosses a defined threshold, often 10%, sometimes 1%, depending on who is writing the datasheet. They write that number down. They put it on the product page. That test is real. The number that comes out of it is real, and it has almost nothing to do with your application. Let me give you the actual physics. The governing equation for how much signal arrives at a receiver is the Friis transmission equation. Power received equals power transmitted multiplied by the gain of both antennas multiplied by the square of the wavelength divided by the square of the distance multiplied by 4 pi. The important term is that distance squared in the denominator. Signal power falls with the square of distance. Double the distance, you lose 3 dB. 10 times the distance, you lose 20 dB. That relationship is fixed. It is not a design choice, it is geometry. So when a manufacturer says their module has a 100-meter range, they are describing a specific point on that curve where their receiver can no longer reliably decode the signal. That point is determined by two things: how much power you are transmitting and how sensitive your receiver is. The industry has historically focused almost entirely on transmit power. More, more range. It is intuitive, it is simple, it is also subject to regulatory limits. In unlicensed spectrum, you are capped. In the 2.4 GHz band where BLE operates, the limit is 1 milliwatt ERP in many jurisdictions, though this varies significantly by region and antenna configuration. You can add an amplifier and push more power, but then you are dealing with current consumption, heat, regulatory compliance complexity, and sometimes FCC recertification costs that price you out of the maker market entirely. Here is what the industry mostly ignored, the other side of the equation: receiver sensitivity, the number expressed in negative dBm, -80, -90, -95. The more negative the number, the quieter a signal the receiver can still decode, and because path loss is symmetric, the signal at the receiver is exactly as weak whether you are transmitting from point A to point B or point B to point A. Improving receiver sensitivity gives you the same range improvement as increasing transmit power with no regulatory implications, no additional power draw on the transmit side, and no thermal management problem. A module with -95 dBm sensitivity and a module with -80 dBm sensitivity transmitting at the same power will have fundamentally different real-world ranges. The 15 dB difference in sensitivity translates to roughly 5 to 6 times greater range in free space, not percent times. Now here is the second thing the range claim does not tell you. It does not tell you what environment it was measured in. Free space path loss is clean. You can calculate it from the Friis equation and it matches experiment well. Real environments are not free space. In a building you have walls absorbing signal. In a city you have multipath, signals bouncing off surfaces and arriving at the receiver phase shifted, sometimes cancelling each other. At ground level outdoors you have ground reflections that interact with the direct path. In the 2.4 GHz band, you have Wi-Fi networks, microwave ovens, and dozens of other BLE devices, all generating interference that raises the effective noise floor your receiver is working against. Every one of those factors degrades the usable range below what the datasheet number suggests. None of them are present in the test environment that generated the datasheet number. The antenna orientation issue is particularly underappreciated. Chip antennas and PCB trace antennas are not omnidirectional in 3 dimensions. They have a radiation pattern, a characteristic shape showing which directions they transmit and receive efficiently. The test was almost certainly conducted with the antenna in its optimal orientation. In your deployment, your module might be tilted, rotated, or positioned in a way that puts your communication path through a null in the antenna pattern. You lose another 5 to 10 dB. It is not a defect, it is physics. So when I designed the BLE module, that 50-kilometer number is not a datasheet estimate measured in a clean room. It is what happens when you eliminate ground reflections and build a receiver sensitive enough to hear what amplification-focused designs cannot. Range from first principles. 2 megabits per second over long-range BLE is not a given. It requires the RF front end to hold link quality at the margins where most modules have already lost connection. This module maintains data rate where others have already dropped out. The STM32WB07 manages both the BLE stack and your application code on a single core. That means no external microcontroller fighting the radio for bus access. The communication layer and the logic layer share one clean, unified processing environment, 57 by 47 millimeters. The antenna is 140 millimeters external and optimized, not a chip antenna making compromises to fit a smaller footprint. The form factor is compact because the RF design is correct, not because the antenna was sacrificed. The module was designed as part of an ecosystem from the first schematic: GNSS, sensors, motor, and battery management. All interfaces are defined and compatible. A unified platform means the integration problem is already solved before you start. The RFOXiA Connect app gives you a live map, sensor data, and a PS5 style control interface, all operating over the BLE link completely without internet. The range of the app is the range of the module. Up to 20 kilometers, no infrastructure. BLE chat runs the same RF link the control layer uses. Text and data between module users, internet independent, at the full range the hardware supports, useful in exactly the environments where internet is unavailable or unreliable. Full SWD access to the STM32WB means you are not locked into factory firmware. The module is open to modification. Every register, every parameter, every behavior is accessible. The AI firmware builder in RFOXiA Club can generate your starting point in minutes. The RTC crystal provides timing that the BLE stack and your application can both trust. In GPS-denied conditions or time-sensitive synchronization tasks, having an accurate onboard clock is not optional, it is built in. Floor of -104 dBm. That is not a marketing figure, it is the measured noise floor of the RF front end under defined conditions. That single specification, combined with an external antenna and careful RF layout, is the reason the module achieves 20 kilometers man-to-drone and 50 kilometers drone-to-drone in real deployments, not laboratory approximations, real deployments, multiple countries. The conventional solution was amplification. I looked at the receiver instead. The physics said it would work. It did.